Let's look at another example of graphical differentiation. So another typical problem that gives us some trouble is a function that's really any odd root of x. Okay, and in general, it's going to look kind of like this. This is what the graph looks like. And what makes it weird is it has this kind of strange kink in it at some place. Now, this kink, of course, could be anywhere in the plane, but for this example, it's right here at the origin. So let's try to graphically understand what the derivative might look like. Now, once we have the actual function written down, a formula for the function, finding the formula for the derivative is pretty straightforward. But let me show you exactly where this comes from a graphical perspective. That is, certainly we can write this as a power, so it becomes a power function. So it's x to the 1/3 power. And we know how to differentiate that using the usual power rule for shortcuts of derivatives. But let's go ahead and see how we can actually draw this graphically. Well, first of all, we know that if we draw tangent lines to this curve at certain places, that's going to be the value of the y output here in the derivative of the function. Okay, as we've done before. So let me draw some derivative lines or some tangent lines to this curve. So here's a tangent line at that point. Here's a tangent line here. And as I draw more and more, you'll see that as I get closer and closer to the origin, both of these tangent lines become vertical, right? Because right at the origin, notice how the function is sort of vertical right there. If I drew a tangent line here, it would be a completely vertical tangent line. So let me draw some more tangent lines that are a little bit closer to the vertical. You can see that's what's happening. And over here, there's one that's maybe right about here. Okay? And so without drawing more to make the graph look more confusing than it already does, let me just see what's happening here. So notice that if I'm on this side of the axis, so for all the positive x values, notice that as I get further away from 0, as bigger, the slope lines kind of flatten out, right? As I get closer, it's sort of more vertical, but as I go this way, it sort of flattens out to 0. And if I went far enough, you'd find that the slope lines become very flat and, in fact, go off towards 0. They never really touch 0, but they get very, very close to 0. So what happens here is the slope, I'll sort of abuse some notation here, and I'll just say the slope, it approaches 0 as x approaches positive infinity, right? Because as x gets very big, the slope gets flatter, so it gets closer and closer to 0. But for the other viewpoint, as I get towards 0, it gets more and more vertical, so it gets bigger and bigger. It goes off to infinity. Right? The slope gets larger and larger. Okay? But each time, notice that here the slope is always positive, right? So the slope goes toward infinity as x goes to 0. Okay? So kind of using some limit notation here. So that's what's happening on this side of the axis, right? On this side of the vertical axis. But a similar thing is happening over here, which is that as I get closer to the origin, hopefully you can see that the tangent lines become more and more vertical. Okay, so the slope is always positive here, right? As I go from left to right, the slope is clearly positive. It's got a positive slope. But it gets bigger and bigger as I go this way, and it gets more towards 0 as I go toward negative infinity. So let me just draw that here, right, that over on this side. So again, the slope on this side of the axis is again going to 0 as x goes to negative infinity. Okay, I'm running out of room here, so I'll just put a comma here as x goes off to negative infinity. And similarly, the slope goes to 0, or make that positive infinity, as x goes to 0. So it does exactly the same thing, except the x values are doing something different, right? That's the only thing that's changing here. But the slope is behaving basically the same in both sides of the axis, the vertical axis, I should say. Okay, so let me incorporate that over here in the derivative, and we'll see exactly what's going on. Okay, remember that when we draw the derivative, we're really drawing, the derivative is in fact the y value, or the output. So hopefully we can see what's going on here. That notice that, by the way, what I should say is the slope exactly at 0 is really undefined, right? I mean, it's completely vertical. So if we have a vertical slope, we usually consider that undefined. So I can't really put any value here. It goes off to infinity. But I can get really close to 0, though, and get a pretty good accurate picture of what the derivative might look like. Okay, so let's do that. So let's start on the positive side of the axis first, positive x values. Again, as I go to positive infinity, the slope is going to go towards 0. Or over here, if I'm drawing the derivative, that means that the y value should go towards 0. Well, 0 is, of course, right here. Right? This is y is 0. So as I go toward positive infinity, it should go towards 0, never quite touching the axis because it never exactly gets to 0. And also as x goes to 0 here, as I go this direction towards 0, the slope goes off to infinity. It's very big. So it's going to go up this way. It's infinity, so the y value is going to infinity on this graph. So a rough picture of that would look kind of like this, right? As I go this way, it's going to go off up to infinity like this, never quite touching the axis, but just keeps getting bigger and bigger. And as I go this way, it's getting closer and closer to 0, never quite touching 0. Okay? And similarly, the same thing's going to happen over here. As I get closer to 0, the slope's going to get toward positive infinity, the same thing. And as I go toward negative infinity, it's going to go toward 0 again. So it's going to do something like this. The same thing, just a mirror image, basically. Okay? And so this is the picture of the derivative of this function. Even though we know how to compute that, if you recall the shortcut method for the power rule, we know the derivative is going to be 1/3 x to the minus 2/3, right? Well, writing that in a better way, getting rid of a negative exponent, this is 1/3 times x to the 2/3 power, or another way to write that is 1/3, 1 over the cubed root of x squared, if you want to write it in root form. Anyway, this we know is the truth because we know that's the power rule from what we talked about before. But even if I didn't know that, I still would know this is really the graph of that thing. And it makes sense, right? Because notice that we can't plug 0 in. If we do, we have undefined, right? Division by 0 is bad. Moreover, we know that as we go in positive or negative, right? It doesn't matter what direction we go. We know that the output is always positive here. Because look, no matter what x is, I got to square it over here. So it's always positive. You have to take the cubed root of it, but it's still always positive because we have to square it inside there. And so it behaves exactly like this. But my point here was to show you that, in fact, no matter what the function is, if we know how to interpret the graph and what the derivative really means, we can always graph the derivative function as well. So this is the graph of the derivative of this red function.